Okay. Here, ramblers, let's go rambling. So the last time we were around this point of the presentation, and basically I did cover a little bit the debugging issues we have. Maybe you remember I just inserted some debug printing and so on, but it was just a scratch of the surface. Where do I? Like here. Of course, the biggest problem we have whatsoever. We do have debugger in comma IDE, of course, but that one for scripts, for modules, but certainly not for the core. There is no way to debug the core with any external tool. So that's all what we have. We have printing of different kinds. Luckily, NQP has say and note routines, which usually simplify things a bit, primarily in Node, because it prints to stdr, which comes handy in a lot of situations, but even they are not always available. So the other thing we left with is our own minds, our own thinking. So the less debugging you need, the better, but you know, it's a wishful thinking. The greatest problem of debugging, of using prints, is the flood of messages we may get. Anybody who ever developed for a big system with a core which is often referred by user code, by front-end code, whatever, knows this problem. When you insert a print, you get like thousands, hundreds of thousands of outputs, lines of output, and it's not only overwhelms your own mind and makes things very much, you know, complicated when it comes to analyzing. But in case of Rakudo, it might even cause breakages in compilation process, because the thing which is not well known is that when modules are precompiled, a lot of useful information is communicated with subprocesses via stdout. So if you print anything to stdout, you're very likely to break precompilation. This is a big problem, and this is another kind of problem, because, as I said, it's not always that you have access to node routine. It's not always that you can use it. Sometimes you end up with using NQP say. Okay, just a few. This op, and NQP say, unfortunately, it outputs to stdout only, and there is no NQP op for outputting to stdr. Sometimes we have this issue. So all we have left with is conditional printing. meaning that we can just limit the set of situations when we print something only to those cases where we really need this information. It still might be a lot, but it helps. And that's what I usually do. So what approaches we have here? I mean, of course, we are all using debug printing one time or another, and we all know all these problems with floods of messages and other kind of problems, and we know that sometimes it's better to limit the conditions, whatever. The reason I'm focused on this because in the core we have a couple of approaches we can use, and it's better to know about them. One of the most simplistic approaches is when you need to debug the core and you don't want any debug prints to be involved while you compile the core, you can initiate debug printing from inside of your test script. And you can do it by using HL symbols. HL symbols is kind of a hash provided by backends, by all backends. And you can keep any values in those symbols, and they're globally available. And by globally, I mean not as a lexical scope or anything else, but globally, where any bytecode has access to them. Access to those symbols is provided with bind HLL sim op and get HLL sim op. So hopefully this example is clear enough. So say we bind to a Rakudo debug symbol, we bind one, and somewhere in the core we check if it's true, if the symbol is true. And when we don't need debugging, we bind 0 to that symbol, and we print nothing. Simple. What is good about this approach is that you can do it anytime, anywhere in your script, so that you can be very explicit about when you want to see the information you want to see. That's it. Very convenient, but not always. There are situations when it's not really good for you. There is another thing. You remember from the first section, I've put specific focus on two things, on lexical and dynamic scopes. And even though I expect anybody of you to know about those beforehand, I was still focusing on dynamic and lexical scopes. That made a specific point here where we need it. And another thing I focused on was that we use the same VM, same backend for executing our core code, our user code. Everything gets executed within the same virtual machine, backend virtual machine. Why is it important? It is important because in some situations, when you do a call into the core, your call stack is continuous all the way down to the point where you may need to debug it. And in this case, you can use dynamic symbols. You can declare a dynamic symbol in Raku code, set it to true, and check this dynamic symbol somewhere deep in your InQP code, in your meta model code, in your whatever, in your group. My apologies. Is it still? Yes, it's still connected. Good. So here is another approach you can use. When you know that some code is part of your call stack, you can use dynamic symbols. There are two ways of accessing dynamic symbols, as you can see. One, you can use it by name directly. And sometimes you would need to use special NQP op, get LexDin, which is basically the same. Actually, when you access a dynamic symbol, eventually it wins down to get LexDin in most of the cases. There are exceptions, but it's not part of this class. And the approach I actually use the most. By the way, let me check out. I forgot probably to mention. Yes. I forgot to mention what disadvantages each approach has. With HL sims, the biggest disadvantage is that you cannot debug your bootstrapping code, and you cannot debug the startup process of your application, because before your script starts, there is a lot of things taking place, and if you need to debug those things, you cannot use HL symbols. For example, it might be a problem when we debug grammar or actions like that. Also, it might still be too verbose under certain circumstances. When you need to debug just some specific part of your code and don't need to debug another one, since those symbols are, very globalish, really globalish, you still would be in a situation when you get output from parts of the code you don't need to know about at this point in time. This approach is much better from this respect, but it still doesn't allow to debug startup and bootstrapping for apparent reasons. As I said, I used to use environment variables. Somehow it works best for me, maybe not for you. I mean, it doesn't mean I don't use other approaches, but this one is most common in my case. Largely due to the fact that it allows me not to get any debug output when I compile the core, and still it allows to get debug outputs for startup and bootstrapping. It's easy to get access to environment variables in Rakudo, meaning that debugging the actual core code, I mean, all the core classes and stuff like that, it's no different from what you do in your normal scripts. NQP doesn't have any special variable for environment, so we use another op, we use NQP getenv hash. A lot of time you can stumble upon code like this in the core. No, better not. Key. NQP getenv hash. I mean, the key could be anything, whatever. It's an artifact of the old times of NQP, as far as I understand. when access to hash objects, low-level hash objects, was only possible with another op at key. It's not necessary anymore. So if you see something like that to access hash value, well, just ignore it. We can do it this way. Just op and then key access to the hash. Okay, so shouldn't be a big problem. And I think the disadvantage of this approach is pretty much apparent. Most of the time, it's also a very globalish kind of approach. So most of the time, you really get that lot of messages. So one of the things I love about Raku is all those tools we have for introspecting data. No other language I ever used has such an extensive set of introspection tools. And I don't say there are no languages, other languages like that. I just never used them. Even Pro, you know, it's pretty much limited comparing to Raku. But NQP as a stripped down version of Raku doesn't have that many capabilities in this area. Lucky if we have access, if we need to introspect a Raku object within NQP code. In this case, yes, we can use methods available on Raku, like gist, .raku, whatever. But most of the time, the objects we deal with in NQP is NQP classes, which, well, best they may have .str method for stringification. Not all of them, mostly those which could be one way or another exposed to Raku code. But when it comes down to really low level objects like VMNull, boot hash, boot array, and lots of no, not really lots, others of that kind, they are not actually NQP objects. Those are low-level virtual machine objects. They don't have any ways of introspecting them at all. So each time you would need to invent something specific to find out what's your data. What does it has? What does it have? Whether it has some values you expect to see in there or you don't expect to see in there, whatever. So what we usually use for introspection? First of all, the most common problem is wrong type or undefined value or something like that. So first thing, we need to find out what type of the data which we have. Luckily, .how is available for any object in Raku land, in NQP land, whatever. Even the low-level objects like boot hash, VMNull, they also have access to how. And even the most basic how object, it has name. So that's what we can do. And you know what? I would try to simplify I should have probably done it from the start. Okay, so we have this way, it's always available. And for example, if we see that something wrong is going on and we're not clear about what's going on, and we suspect, for example, that we don't have an actual object or high-level object, but we've got something like VM null, we can find about it using this approach. Of course, next thing we would need to know if it's concrete object or not. This is simple. This NQP-op tells us if our object has a concrete value, and NQP-op, which is not documented, but it is there, and it is used actually to generate output of .which, if I'm not mistaken, object ID. Object ID provides you with unique and prominent ID your object has. So if you need to find out if two objects are the same, this could be the best way if you print your debug information. Those are the most basic means of introspecting. Yes, the thing I should have started this part of today's section as well as I started the previous one. I should have mentioned that please remember that this class is not something for in-depth studying. This is just an introduction to provide a hand to cross this threshold we need to cross over to get into the core development. Because this threshold for some it's pretty high for some people. And for those who has some experience, I hope to provide maybe some additional information. So the point I needed to mention it now is that the more experience you get while developing for the core, the more means of introspecting you may find. I mean, we're not limited to this only. Different situations may require different approaches. Now we are finally around NQP. It's not much I'm gonna tell you about NQP anyway. Just a few things. On several occasions, I mentioned that NQP is a simplified version of Rakudo. How much is it simplified? You have no idea, because there is no documentation. The only way to find out is to play with it, try it, and read source code you see around. Best, of course, if you can get through the tests provided with NQP. I'm not that good. I'm not that patient. I started immediately using it. You know, trial and error approach. And I must admit that not so long ago, I realized that turns out, oh, we have multi-dispatching in NQP. I didn't know that. So it is very simple multi-dispatch, very basic, but it is there. it can be used. And later I found it in the test suite. And this is my primary approach, was trial and error. If something doesn't work, NQP would remind you about this. And still, yes, NQP is advanced enough to provide you with the best programming techniques we didn't have like 20 years ago. So it's an advanced object-oriented language with advanced meta model, though simplistic, but still advanced, because it doesn't mean that it's somehow limited in its functionality. That functionality perhaps is not developed for NQP because there is no need for that, but it is possible. Not sure if anybody would ever improve meta model of NQP except for bug fixing, but well, it's possible. And most of all, best of all, NQP has built-in grammars, some other goodies, but grammars. And that's what makes NQP a compiler building language. That's what makes NQP the bootstrap language of Raku. So welcome, use it. Grammars are not so different from the documentation we have for Raku. It lacks a few features, but really just a few. A little bit of terminology. HLL, it's high-level language. What does it mean in our Rakulang, in the core? There is no strict definition for it. Basically, it might be said that NQP ops are not HLL, not high level. Bytecode, of course, not high level, but NQP is. NQP is a high level. And by the way, linking back to binding symbols, notice this Raku here. When you bind a symbol, you can specify what language has access to this symbol. So it's not that globalish as I said, because if you bind it to NQP, you don't have access to the symbol from Raku, unless, of course, you specify that you're looking for an NQP HLL symbol. The point is that here with this op, you can clearly see that HLL relates to NQP as well as to Raku. I used Raku here, but whatever. It could be NQP. Yeah, here. So, as I said, Raku is HLL and NQP is HLL. The point for me to mention this this term here is because I should have prepared. Well, it's not really. Because if we look inside NQP source code, we can see that there is HLL subdirectory. It's a subcomponent of NQP, and this subcomponent provides basic services we use in higher level languages like Raku as well. For example, we have a grammar And grammar class is named HLL grammar. I'm sorry for the slowness, but Zoom is really something. It takes a lot of CPU. And then, as you can see, NQP grammar itself, it inherits from HLL grammar. Come on, please. And despite the expectations some of you may have, despite the fact that NQP is a simplified version of Raku grammar, +6 grammar for historical reasons, is not inheriting from NQP. It's also inheriting from HLL grammar. That's because some minor peculiarities of NQP makes it easier to recreate the grammar from scratch rather than get around those peculiarities. And coming down to Raku AST, we can see that the new grammar Raku is going to use and is using already is also HLL grammar. So we don't reuse the legacy Perl-6 grammar, even though some code may be migrated with copy-paste. But again, the differences in approach to Raku AST and to the legacy base, they make it reasonable to not to reuse the old grammar. Now back to NQP for a little bit. Some most notable differences you would need to know is that routine declaration always requires a signature. So you cannot declare full without parentheses. Sorry, my pronunciation. I have some issues with my throat, and I'm prominently suffering from dry mouth today. So it makes things harder for me. Invocation usually done with parentheses, but they are not actually mandatory. So it was a mistake on my side to provide you with this example, the torch full. It could be called without them. NQP doesn't have containers. I mean, you know what container is. You know, we have scalars, we have arrays, we have stuff like that. NQP doesn't have containers whatsoever. Therefore, we don't have assignment semantics in NQP. We only have bindings. So any symbol in NQP, it's a direct binding to its value. And even though on some occasions you can see something like that, like this, okay, I don't caps lock. It's okay, whatever. It doesn't mean that you have a scalar. It just a workaround, NQP workaround, which allows it to use increment directly on a symbol. Because in Raku, this operation works totally different way. If you bind an integer to a symbol, you cannot use double plus with it because it will complain about immutable value. This binding actually, it's my biggest problem because I permanently forget and always tend to use assignment. Many high-level routines you have in Raku. We don't have in NQP, so sometimes you have corresponding NQP ops, and sometimes you have to simulate them if you need something like that. I don't specifically mention what routines because there are a lot of them. There are too many of them. And we don't have the extensive type system in NQP apparently. Most of the time we are bound to the native types like int, str, and so on, num, whatever. We, of course, it's an object-oriented language. We can use classes, we can instantiate them, we can use objects, no problem, but there is no type checking as such. So if you put a class into a signature, something like this, it doesn't mean that .v would be checked for type classes if it's an instance of this class or class itself. No. So it's mostly something you can use for yourself, like a node, but it doesn't work. This works. This can be used. NQP ops. A little bit confusing subject because even though at the first glance it seems like, okay, yes, the kind of syscalls, you can use them to call into the core and do something you need to do. But they're not syscalls, as a matter of fact. For myself, I don't even have a good definition for what ops are, because sometimes people expect them to be to represent opcodes of your virtual machine, of your backend bytecode executor. Some of them are, it's true, but not all of them. Because some ops, they're actually implemented in NQP itself. And they're wrappers, kind of wrappers around other ops, or, well, they just provide you with some functionality. So the only thing we know for sure about NQP ops is that they're somehow implemented by the core, and they're available anywhere. You can anywhere in NQP or anywhere you in your Raku code where you use NQP programmer into your code. That's all what is guaranteed about ops. Did I mention? No, not yet. So all you need to know is that they exist and how you can use them. Another problem, it's not enough to know that they exist. You need to know how to use them. And unfortunately, not all NQP ops are documented. There are different reasons for this unfortunate fact. So let's not focus on this, but sometimes, like for example, object ID, I found it experimentally. I needed to find out if two objects are the same or they're different. I needed to know, to get more information about them. And I stumbled upon NQP object ID, and I just instantly got the understanding of what is it. But things are not always that simple. And no, it's better. Like this one. Can you guess what it does from its name? And it's not documented. And really, without some help from IRC chat, I would never find out what it does. This opcode turns off serialization of any object created while this op is in action. So like when I bind something into this attribute, this code is not serialized and you will not find it later in the bytecode, meaning that the value in this attribute, it always would be a purely runtime value. It only exists at runtime. So if your object gets deserialized from a file or from any other source of bytecode, this attribute would be empty until something happens. So if you stumble upon a node which is not clear to you, it's your best approach is to ask somebody. But before asking, you have several other options. Wait a second, did I mention it? How come? I'm sure it's somewhere. Okay, before asking, we still have some documentation. In NQP source code, we have this ops markdown file. And usually I don't treat it directly because markdown is still a markdown. And what I do, I just open NQP GitHub repository. Yeah, I would avoid opening it right now. And read it online, because on GitHub you get it in formatted, in pre-formatted way, so it's much easier to read, and so on and so on. Anyway, we have this documentation, and yes, actually we have chat. So what I can do, it's not necessary to open this page, but I can give you a direct link to it, so you wouldn't need to So normally I open this link. There are also some opcodes which are specific to Raku itself. Since the legacy Pro6 name, they all start with P6 in their name. So if you see MQP : P6, it's a Pro6 specific opcode, and it's not available in NQP, but there is one specific NQP code of Raku core code. It is considered as a Raku, part of Raku, and therefore those opcodes are available for NQP code in Raku. Take it as granted. You will find, I hope you will find out more about it later, but there is no way you can get access to P6 codes in NQP source code, but you have access to them in Raku code. So, okay, we are lucky and we found an op description in the documentation. What if we're not? And other way around, what if we need to know the exact way an op is implemented? Sometimes it's necessary. Most likely, locations where to look for them are in virtual machine backend code. In case of more, you can see the full path to the file where ops are declared in NQP. So more step. Here we go. And we can look for lines like this one. So what we see here is a declaration of an op, a list op in this particular case, a list of numbers, of nums. The way it is declared is by using a special method which takes a name for the op, and it takes an actual body of the op in a form of code object. And then we have an implementation. Some ops are, as I said, probably not in this file. Some ops are really direct mappings into the bytecode operations. Those are declared a little bit differently, and you will find it later. It's not a big deal. Pro6 ops or Raku ops, for that matter, whatever, they're declared apparently in Raku source code, and file name is different. It's ops NQP. For JVM backend, the path and frankly saying, well, I'm so rare guest in JVM world that it's not always easy to recall where things are located. Yeah, I think. Yes. Found them. What I love Java for is for its conciseness. One of the shortest paths in my life. As you can see, in Java, ops are declared using Java code. So we have now start, whatever. Let me not focus on this. So eventually, as I shown you, when you're looking for a declaration of an op, you can simplify your task by grabbing for registration methods, add core op and add HLL ops. My apologies. Come on. Oh, okay. I'm sorry, but with so bad performance CPU, it's really a headache. But it's not that important. Now, I hope the background we currently have is sufficient to proceed to another big component of the core, to the meta model. Raku meta model is located under Pro 6 currently. I think it will migrate later at some point. Not sure when, but so far it is there. Meta model consists of several kinds of interfaces. The biggest part of it is so-called house. It's classes which are implementing behaviors of other classes. Smaller part are different kinds of helpers. Those could be some roles consumed by how classes, or there is one helper which actually stands aside. It's named metamodel configuration, and it's a class which provides an interface to configure different aspects of metamodel behavior. Let me skip this part. It's not really relevant. Oh, here is my grep came up with some results. So as you can see, and if I need to find CW, it's not here. It's a direct mapping, so this object cannot be found. Okay. Again, my apologies for being not a little bit distracted today. As I said, I have a little bit of issue. So, if something is not clear, please don't hesitate, ask your questions. It's no problem to interrupt and get some unclear things resolved sooner than later. Please awake. So I'm focusing on, because it stands out of other metamodal classes. It might be a little bit confusing. So let me show you by example what it does. For example, this method sets dash type. During the bootstrap, where am I located? Bootstrap.c, bootstrap.p, here. During the bootstrap, when we stub our classes, we must remember that each class on its own is a package thing, means that it has a symbol table. And a symbol table has to be backed by some other kind of object. And this is what happens. During Bootstrap, we specify which class would be responsible for stashing symbols on our client. We can replace stash with something else. This part of behavior is configurable. And this is why we need metamodal configuration. There are some other aspects this class performs. The class itself is never instantiated. It's used as is. And all the configuration values are kept in local variables. So they're global by definition. There is no way you can use different stash type in some local place within your program or your alternate implementation. No. Is it everywhere or nowhere? And another thing, this class implements is not defining a behavior, but providing a standard behavior. The things which are low-hanging fruits and which you can start doing for the core. Around a lot. NQPDI and some kind of message. And at some point, if something goes wrong about the runtime, you can get an error message coming from the core telling you that, oops. But what kind of oops is it? It's an ad hoc. And what if I want to catch it and analyze later? No, it's not an exception as such. And this method, throw or die, it's a wrapper which allows our NQP code to throw a real exception when it's possible. And by when it's possible, I mean that exception classes are not always available. Sometimes because it's too early, sometimes for other reasons. Well, it's not always that we have access to exceptions. So this method takes care of this. If it's possible, it pulls in an exception class and uses that class to throw an exception, or it will fall back to NQPDI with some simplistic message. And I started doing this work a while ago of converting plain NQPDIs into exceptions, but it's in Bootstrap already. Here is what it looks like in a real code. A little bit wordy, perhaps, but that's we need it this way. Still, it's very simple to use because you specify what exception you want. You specify what message to use if the exception class is not available. Best if this message resembles the message which would be produced by the exception class, but not necessarily. And then you specify arguments to be passed to the exception constructor. So eventually, chaos impossible. Oh yes, this is certainly my part, of course. Chaos impossible. But we still have a lot of pieces like this. NQPDI here, NQPDI there, inconsistent bind result. It could be replaced with throw or die. And this would be a very good entrance point into the world of low-level Rakudo code, like metamodel or bootstrapping, because if you find an error message, first thing you would need to do is to find out what exception has to be thrown. And to do so, you have to find out why this error is going to be thrown in first place. And by finding that, you would need to analyze the surrounding code and find out what it does and how it does it. And of course, it's a great way to study the core code. So it's a kind of a low-hanging fruit, which would bring a lot of improvement to error processing in Rakudo. And it's not hard to do. Now, another a little bit specific class is, oh, sorry, class role, build plan. Okay, build plan. Yeah, you know, sorry, forget about it. If we get time, I'll get back to this part of metamodel data. But for now, I just want to show you the most typical example of how things work in metamodel, because class how is apparently the most used class around. Yeah, as you can see, it consumes a lot of roles in first place, so many that they don't even fit into one screen. Each role provides its own functionality, of course. It doesn't inherit from any other metamodel class, and at this point, I'm not even sure if we have a single class which would be inheriting from other classes in metamodel. Each how implementation must provide a few key APIs. First one, it has to specify what kind of type objects it creates. Archetype specify what functionality is how to tell. Again, I'm sorry. So in this case, nominal archetype means that our class is something nominal. Yeah, it's something which has concrete value, can have concrete value. Actually, we can do it other way around. One level up, then here, then how we can pull in NQP, and we can pull in our archetypes from NQP. This is where they're defined. So let me skip this part again. Just know that if you need to know more about what archetypes are, what they are providing, you can always find it in NQP source. The only thing I can do is to show you the difference. If we look at into the implementation of roles, we can see that it's also nominal, but it is also composable. Composable, and parametric. If we go back to our class implementation, we see that it's just nominal, but it's not composable, not inheritalizable, but inheritable, and it's not parameterizable. Sometimes it's confusing people because Raku implementation allows to parameterize some classes, like hash, for example. But it's a trick. It's rather a trick, but it's not something inherent to our standard class implementation. The next thing, of course, we have to provide new method, because any how class must produce an object which would be responsible for a specific type object. So this is all. This is something we all must know already, that when we have a type object in Raku, this type object is backed by a concrete object from MetaModel. Concrete. Sometimes it gets people confused. And this type object, it's actually created with new type method, which is also has to be provided by any how class in the MetaModel. And the last thing, which is more or less common, is that any type object passes through several stages in its life. It gets created, it gets set up, and then it gets composed. And when it's composed, it is considered finalized and ready to be used. No type object can be used before it is composed. Used in a normal way. Let's put it this way. That's it. That's the four things which ought to be provided by any how class. The remaining depends on the functionality your class is implementing. So how classes, they are public interfaces with this respect. Helpers, I mentioned. And that's basically it. I'm not going to put much focus on meta model because it's probably the most easiest part of the low-level code in Raku. I mean, the core itself is the easiest in my point of view because it's implemented in Raku itself. It's familiar. And meta model next in complexity because you have direct access to it from Raku code, and it's easy to read and it's easy to debug. This is where I personally started back in 2018. Yes. Now we come to the most complicated thing from the point of view of NQP code, because speaking of complexity, we have optimizer, and then we have the backend, especially more VM, which is so complex, I don't even go there. I mean, I can do some things in more VM because I still remember my old good days of C programming, but some things they do in more VM, they're kind of magic to me. So the compiler. The compiler is not what some may expect it to be. Compiler class doesn't actually compile. It's a wrapper. It's the class which is responsible for orchestrating other components of the compilation process. There is no one such thing. You can say this is the compiler as in Perl, where you have C code which does everything. They have their own structure inside, but from outside you have just, this is Perl, this is the compiler of Perl. Here things are different because we have direct access, easy access to NQP code, which we can read out of the box. If we know Raku, we automatically know NQP, except for NQP ops perhaps. So when we enter this source code, we immediately start to understand what's going on, so we can more or less understand some concepts. Compiler is located in compiler NQP, apparently. And here we go again, HLL. Compiler inherits from HLL compiler. 2. So HLL is our source of basic functionality, which other languages can use. For example, if at some point somebody decides to implement, my apologies for mentioning this word here, Python in NQP, then Python compiler would be inheriting from HLL compiler for sure. And I expect Python grammar to be inheriting from HLL grammar as well. So, and the compiler is using our grammar, it's using actions, and it's using optimizer to actually build the byte code. Let me see my notes for this. This is for later. Grammar, yes, this I mentioned that it's. And the last thing, all these 3 components are using is Vault. Vault is a class which is providing services to our parsing process, actually, and optimizing process. It's hard to say what exactly Vault is about. It just glue for other components. It provides storage for symbols. It provides ways of managing symbol tables. It provides methods to generate some standard code for different standard situations. I mean, it does a lot of things, and it's hard to say exactly what Vault is. But who cares? It's going away. Rakudo AST will not have it. So perhaps if you decide to fix a bug in the legacy code, you may still end up somewhere inside Vault code. But maybe it wouldn't happen. I just don't know. What really matters here is that when we speak about the optimizer, then we must remember that we speak about a static optimizer. We speak about a component which changes the code produced by actions and grammar in a way to make it more efficient, like stripping down some operations which are necessary when we know they're not necessary, or so on, so on. I'll get back to it a little bit later. And now we need to take a brief look into the compiler first. There is not much to see in it. Oops. Compiler. Because, well, it's a class like any other class. This part is gonna change soon, I hope. Unfortunately, Liz is not here today. I would have some good news for her, because I think I found an approach to have a different versioning scheme for Rakudo, which wouldn't depend on the legacies v6.c, v6.d, and so on, and still be functional enough and flexible enough. So these attributes, they're going to change soon, whatever. What is useful here is this config method. It provides some information. I will show you what kind of information is it a little bit later. And then a bunch of methods. I mean, just class like any other class. At some point, you may want to trace it down, but well, with the same probability, you would be tracing down Rakudo AST compiler. It's not part of today's class, but at some point we'll get there. Command eval is the one to know about this, because this is the entry point into our user code. Command eval is the method which takes care of the actual compilation process, storing the bytecode, invoking it, and so on, so on, so on, so on. So whenever you go, if you do a full backtrace of your code, you will find command eval somewhere at the bottom of your stack or top of your stack. Somehow I always miss top and bottom in the stack, which is top and which is bottom. Whatever. And optimize and so on. But the compiler itself, it has to be invoked as well. And this is where we get it involved. This is the root of all Raku runtime. So you can see the familiar main sub, which does the preparation process. What useful can we pick from it? Command line. Here it goes. Yes, of course. So before main gets involved, we need to create the compiler object. So we create it. We specify the name for it. Remember high-level symbols. Remember the Raku name used and stuff like that. So here we define our language name. Here goes our request part, but we currently get past it. Then we specify which grammar and actions class we're going to use to compile our code. So as you can see, when request is activated, we use different grammar and different actions from the case when we use legacy. Here we just define command line options. We provide some useful symbols to the rest of our code. And then we come down to the main, which gets invoked automatically, parses command line, and invokes the compiler object. Eventually, we came down to the root of it all. We know where it all started. It was the first day of creation. But main QP itself is not used as is. I mean, it's also just a part of something bigger. Wait a second. Sorry. Oh, it's not so often I get in here. Okay, anyway, version, is it? No. Okay, anyway, this is the file I wanted to show you. When we start, we also need to know some parameters of our compiler. And this is the file where you can find those parameters prepared. Remember that config method from compiler? Just at the beginning here. This is what it contains. This is where we get things like current compiler version, the default language version we use when language version is emitted by user source code. We know what language versions do we know about, do we support. So say, when in our code we do something like v6d preview, this version is actually matched against one of these values. As you can see, D6D preview is available. But if I do a mistype of some kind, this version is illegal because it's not configured. So this hash is a little bit specific and we can skip it. This one is specific and it's gonna be gone, and some path information. So sometimes it's a little bit confusing how do we know what language we are currently compiling? Where do we get it from? This is where we get it from. This is the source file where it's all located. But don't modify it, because as you can see, it's located in gin directory, which means it was generated. I have shown you this version of it because it's prepared and it's readable. Here is the template which was used to generate it. So as you can see, I could have shown it to you, but it's not of much use. Most of this file is produced by configure PL script, or rather by the modules it is using. Okay, anyway. So this part I have done already. I did show you command eval, but the actual entry point is command line method. You can find it out later. It's not of much use. Just here is just how things happen. We get eval method on compiler, then eval calls compile. When compile is done, it is expected to return some bytecode, and that bytecode gets invoked. So just general path of events. Yes, this is really important because also remember last time I mentioned that there are cases where it's hard to trace down the code because things get invoked which are located somewhere in the backend implementation or in NQP and so on and so on. So when we speak about the compiler class, most of its functionality is already implemented by HLL compiler. So when you trace down, when you're looking for when this shit is happening, why is it happening this way, go check out HLL compiler in first place. This is where you're most likely gonna find the details you're looking for. And now it gets better and better. Because we enter the territory where there are just few, if any, docs available. So all we have is our imagination and the source code. So even comments are pretty scarce in those waters. This is another task I would like somebody to take or at some point to create documentation for those internals which are not well documented. The and still, those waters are so wide that I hardly can manage to introduce you to all of them. But let's get to the most interesting parts and those you need to know about before going any further. As I mentioned it earlier, grammar is inherited from HLL grammar, and its syntax in NQP, it's almost the same as the syntax in Raku. So we don't need to focus on its syntax, and we better go on and proceed to the logic of it. First of all, grammar is very heavily based on dynamic variables. Let me show you what does it mean. When we enter into the grammar, the first thing we start with apparently is stop method. This is something we all know about, but the first line of code is nothing else but declaration of a dynamic variable. These two are the key variables across the grammar itself because they define the grammar. We need them for one very serious reason. In many cases, the self instance you have here within the top, because grammar can create clones of itself. In which case, when a clone is created, you don't have access to grammar attributes, initial attributes, so you cannot use them. This is where we get this access from, through this dynamic variable. Then we go down top, we can mostly skip, except for one thing, because all those preparations it does, we don't need to focus on them at this point. What happens at the end is that it invokes compunit method, and as we all remember, tokens and rules in grammar, they're actually methods. So I don't remember, is it token or so just compunit. And again, what we see here, we start with nothing but with declaration of tons and tons of dynamic variables that we're going to use later. The reason for this approach I mentioned above is the way grammar works. We don't have access to the attributes, and the reason for this implementation is, for example, when we do backtracking, it could be auto-threaded, so that if you have a couple of alternative paths, each path could actually be tried alternatively at the same time in different threads. So either you need some complicated concurrency to support this, or You can just create clones which would do all the work, but they still need access to the information previously collected. And the best way to get access to this information is to reach it out through dynamic variables. That's it. There are some other reasons for this approach, but still. Oh, some more dynamic variables, and some more, and a little bit more, and a few at the end. And only then we start doing some actual work. Grammar itself is responsible for preparing the environment. So most of the work is done to compile our code, is prepared by the grammar. As I mentioned, compiler object itself is just orchestrate things, but it doesn't control them. It's the grammar which controls the actual compilation process. So first of all, it sets up language break. Anybody needs an explanation of what language break is? Okay, anyway, I have to remember about the future online audience, which could be about people who could be watching this later. So language break means that our Raku language doesn't have a single syntax. It consists of different languages, sub-languages, or as we call them, slangs. Those slangs are here in the list. Regexes, they're separated by a specific compiler. Pro6 regexes, oh yes, I missed a word. Pro5 regexes, Pro6 regexes. Quotations. By quotations, I mean strings. Strings are actually a sub-language in Raku. They are not a part of its data structures or whatever. And of course, it is Raku itself. Here we go. This is what happens here. How the language break works, again, it's a little bit complicated subject, and I may miss some parts of it because last time I've been swimming in these waters was maybe 2 years ago, so some details could be missing. But generally think of it in a way that, for example, we encounter something which looks like a start of a string, we just invoke another grammar and let it parse the remaining part of the string. Something like that. Next thing the grammar does, besides some other preparations, where are you? Here we go. It creates the vault object. Also, as it was mentioned earlier, is that vault is specific to the legacy implementation, to Pro6 implementation, but as soon as you get into these waters, you just need to know that vault belongs to the grammar. And I know that a lot of modules, and I'm guilty of this myself, they're using this undocumented symbol $*w in their code to get access to some services of the world. And those who used the symbol, they know very well that the only time when you have access to it is begin time, because begin time is the time when grammar is alive and kicking. As long as compilation of your code is done, grammar is gone and world doesn't exist anymore. So this is where we get it. Okay, the other stuff here is a little bit specific and a little bit out of the scope of today's talk. So let's just recall the symbols we just saw and just don't mix up. $*lang is grammar. The hash lang is the current language braid. Slangs are not properly supported yet by the current implementation of Rakudo, but in the future, I think if you need to find out what slangs are installed in your system, you would be probably inspecting this hash. Yes. This is a good time to get back to grammar NQP and using this little knowledge we already have about the comp unit. Let's see what happens with the rest of the components while we compile, while our code is being compiled. So the actual person starts with this token, not with top, but with comp unit token, because compilation unit is the thing, you remember, I was mentioning it, is the thing our compiler knows about. It's the unit it operates with. Comp unit itself, as a rule, is not very complex. Well, it starts with lang version. This is where our language pragma gets parsed. And this is why it must always be the first one, the first statement ever, because apparently before you need to know what language it is written in. And then any comp unit consists of statement list. And that's it. The rest is done by the statement list. We get one statement, we analyze it, we do something about it, and go on and go on and go on and go on. And when it's all done, we probably report any warnings or errors collected during the process if they are not fatal for the person itself. So that if we can say, if we have a couple of errors, we can report as a single bunch, so that we don't waste time on recompiling our code again and again to find about the next error, but we can fix them all at once. So we try to collect them, and this is where we report them. And then we clean up, and we are ready. We have some kind of bytecode. But where do we get this bytecode from? And we get it from actions, of course. This is how grammars work in Rakudo. Something I miss here. Yes, of course I miss. Yes, my apologies. Even before the length version gets parsed, a very, very important stage takes place. We need to prepare our environment, compilation environment, to compile our comp unit. And this is how it's done. Just a chunk of NQP code, which invokes comp unit stage 0 method on the vault object. So now it's time to visit the vault object. Unit stage 0. And check out what has to be done before we can parse anything. First of all, we create symbol tables for our comp unit. When you refer to global symbol, you actually refer to this, one of these. We have the legacy implementation is using two frames to implement a single comp unit object. One is unit outer, and one is actual unit. Unit outer is a little bit of a hack used, for example, by REPL, by our command line processing. So most of the time we just ignore it, but we need to know it exists. Here is our primary comp unit symbol table. Then we take the compiler, and here goes next outer. Let me skip most of it. Next important thing. We need to preload setting if it's specified on the command line. See, this is apart from our make file, where we compile a core file, and we define that we need to use null setting. This is a special setting name which gets translated in some actual file and so on, but the reason for this special file name is because initially, of course, we don't have any setting available. When we compile our core, we compile our core setting, and it's not ready to be used at this point. So we cannot define, especially for core C, which doesn't have any outer. Core C is our top level setting. It just exists on its own. So here, as you can see, we check out if it's the initial stage of compilation, if we actually compile our core setting, and we do some preparations. They are not relevant at this point because it's too many details, but just something we need to know that before we can do anything, we need to find out, do we compile core setting? If not, we're gonna do things slightly different. And this is where we leave a mark to ourselves, raise a flag that we do compile core setting. Then we prepare setting revision, because as you saw it, the name null, it contains a version number. So we process especially, and then we know what settings to be preloaded for the core we compile currently. And then we're ready to proceed. Okay, we are done here. We know what we compile, and we know what we can have to compile this code. Then, only then, we check our language version requested for the code, user code. And when we know it, we call another method on the vault, which is stage 1. And this one was a little bit terrible for me initially. It's only at this point we actually load our second file. This happens in this method because in order to know what setting to be loaded, what version of the setting to be loaded, we need to know either what core file we compile, if we do compile a core file, the core setting, or what language version is being requested by the user. And only when we know both of these things, we can decide which version of the setting file we need. And here we load it. Briefly, not to focus on the process of second loading, I would just mention that at this point, Vault simply wraps the code we started compiling into this loaded setting file. It sets us as a lexical outer, and it makes a note that this is the bytecode file to be loaded when this compilation unit is loaded by module loader. It sounds a little bit complicated, but simply make a note that there is no some special code which inserted somewhere which actually loads one module file for another module file. There are entries in your module file which are specifying which other module files, bytecode files, are to be loaded before your bytecode is being executed. Then we can skip a little bit of this part. Now, we cannot skip it because this part is really crucial. Speaking of meta model, at this point, what we do, we actually set up which meta model classes are responsible for what kind of objects in Raku language. Set how method on lang specifies that, for example, for class, we use class how, for package, we use package how, for module, we use module how, and so on, and so on, and so on. You can find a little bit more about this process by looking in the documentation for export how it is documented. So, and you can find export how in our bootstrap file, you can find it in some other locations. And the last thing we do for comp unit before it's ready to take in all the code it contains, we set up special symbols. We set up global, which is the symbol table of our comp unit. We take care about export symbol. We set up special variables. Some more special. That's, you see, a lot of work has to be done before we are ready just to start compiling things. And when we are ready, we actually install those symbols in our symbol table. So basically, only at this point, we are ready to further compile our code, because we have all the necessary information to find symbols in this meeting, to find symbols probably in our local comp unit symbol table, and so on, so on, so on, so on. Load dependency task. This one is also interesting, but a little bit preliminary for this moment. But anyway, comp unit is pretty complicated thing actually. It's not just the code we inserted into the comp unit. It also consists of some special hooks installed by the compiler. And those hooks are necessary to take care about the integrity of our symbol tables and some other stuff when comp unit bytecode is serialized or deserialized. And to make things even more complicated, deserialization takes place in two cases. It takes place when we load a bytecode file, and it also takes place when we invoke begin blocks, for example. When the begin block is done, before it's when a begin block is encountered, before it's invoked, it has to be compiled, and when it's compilation done, it has to be deserialized as well before it can be executed. And begin block as such is a comp unit on its own, actually. So if you didn't know this is just a funny part of how things are implemented internally. And as such, it needs to do some deserialization tests before it can be executed, because there are complications about how begin block can access symbols from the outer compilation unit. So this is basically it about how compilation starts. The rest, I better left off for your own consideration, because really it's a subject on its own. It's a big subject. Okay, Vault, what can be added about Vault here? Basically, I think I mentioned all those aspects of Vault already. You can functionality, yes. So I have the only definition I have for the Vault object is that it's a Swiss Army knife of the parser. Somebody of you was curious about QST. QST is an abstract tree, which I think you should know about. Why is it QST? Abstract syntax tree, sorry. Why is it Q in first place? If you know the history of Perl 6, it was started with a virtual machine named Parrot, and Parrot apparently gives us P letter, And so abstract syntax tree for that virtual machine was named PAST. Parrot itself turned out to be a big failure. So we moved on. I wasn't there at that time, but anyway. More VM has popped up, and the syntax tree has been renamed to the next, moved to the next level. So P, what are our next level to P is Q. So we have QAST. And still, when you look inside grammar or actions, mostly actions and world, you still can find a lot of PAST variables. Those are remnants from the old times. QST is documented. I would say that the level of documentation is not sufficient, but it is good to start with. Source files are located in NQP. So there is no QST source files in Raku code because they're really low level stuff, very low level. Yes, I mentioned it. AST is apparently built by actions. There is nothing new here. And the key thing to know about QST is that it's not immutable tree. It is mutable. The fact that it is mutable lets our static optimizer to operate in it and modify it. So static optimizer does not work with the bytecode, but it works with QST tree. This is just if you didn't guess it before. QST is directly translated into the bytecode, and if you ever wondered where it happens, then for more VM, it's done by NQP actually. And it's done by this class. There is also regex compiler, but this is certainly out of the scope. And I'm not sure I would ever get to regex. I don't even know how regexes are compiled into bytecode. Have no slightest idea. I've never been there. Sorry. About the same thing when it comes to JVM. In JVM, we just compiler and QP. A little bit about QST structure. It is a set of classes. The root class is named node, QST node. It's barely used as almost any base class. A few QST classes inherit directly from it. Those are native value classes, like integer value, numeric value, string value, and B value. It's hard to say what B stands for, binary maybe, I don't know, blob, whatever. It has a little bit specific meaning. And also WVAL. WVAL, Okay, whatever, it's also a value. For now, let's just keep in mind it's just a value. It's wanted. W stands for wanted. Rest of the nodes, they inherit from node, but they also consume children role, which means that they can actually be, those are leaves. I mean, they can only be endpoints of our QST tree. Rest, they could be branches, and they can have subnodes on them. Here's a more or less typical example of QST tree, as you can see it while dumping. On the right side, I provided named arguments for QST class constructors. So you can, for example, do QST block.new with name test, and you get a block node which would have name test apparently. What is important to know about this tree? Don't actually pay much attention to the node names for now, except for statements. This node is not represented in the bytecode as such, but it is used as a container which doesn't create a lexical scope. When we speak about a lexical scope, we speak about a block node always, because block is translated into a bytecode frame. Why do we need statements then? Because statements allow us to logically organize our QST tree into blocks. Here on this diagram, you can see a typical structure of a block QST node. It has two statement blocks, or it has two childrens. It would be more correct to put it this way. This one is a symbol table. So if you declare a variable in your code, it always goes into the first child of the block of the lexical scope in which the variable is declared. You can see it with this var here. And this one is the actual body. It's the code which gets invoked when we invoke this frame. It's not a big problem to put some actual code into the declaration. You can, this pop, for example, you can move it here and it will work, but you better don't do it. But at least, not to confuse your fellow developers. Why is this structure? Actually, I'm guessing here. I never asked nobody, but the point is that we can have a variable, a symbol declaration anywhere in our code. And inserting it anywhere is pretty much, inconvenient, to say the least. So what happens if you declare something in the middle of your code block? We know that the first child of our current lexical scope block is the symbol table, and this is where we push our new symbol into. We just go there and push. We don't need to do anything. It's simple. And we get it there. And it's easy to find it. It's easy to manipulate the symbol table. And later, it's easier for the compiler to build those symbol tables for you. Because eventually, this part, it becomes a static part of our frame, and it's immutable. You cannot modify it at the runtime. Well, actual code here, as you can see, op that's what this is our representation for this notation in our high-level language. Same about the op below. It's NQP, bind into symbol full, lexical scope, value 42. It is possible to dump QST3 using special dump method on QST node. Well, I know it's somewhat late already, but and we are actually beyond the 2-hour frame I defined for myself for the previous class, but we are close to the end of what I have ready. And so I hope it's okay for you. Here is a typical example of a dump we get with that method. And here we can see the key points, the key elements of our compilation unit, actually. As you can see, a compilation unit itself is translated into a block node. You can see that it is a compilation unit by the name here. And that's basically it. That's all we need. And also, as you can see, its first child is statements, and it consists of declaration nodes. As I told you, this is the first child. But the declaration doesn't end there, because this statement, it's also a declaration, but it is specific, because this is a declaration for a sub, for a routine named foo, well, as usual. And this routine, as you can see, it's a block as well. So our comp unit is actually a code object as well as any routine, just a little bit specific code object. But with sub, with the routine foo, we can even more clearly see the structure of our block, because here we have the declarations, and here we have the actual code, the second child. As you can see in this case, the second child is not statements. The reason for this is because any routine eventually ends up with type checking of the return value. And the type checking is done by P6, by the way. Notice the name here. By a special op, P6 type check return value. So we don't need to use any statements. We just insert one single op, but it doesn't change the fact that here the body starts. Come on. Yes, it's in history. This is the command line which produced this dump for me. So notice the start. You see the dump is quite extensive, so it's not easy to fit it into the presentation. So here's our type check return value. And only here we see the statements. Only here our code block actually starts the execution. Anyway, I believe we are done with this part and we can proceed to the examples. First of all, I have to mention that QST is NQP, an NQP entity. By that, it means that it's not easy to use QST objects with Raku. It's possible, but it's a headache. So examples are written in NQP, and I'm using NQP to show them to you. Next thing. Okay. It's not a big deal to create a QST tree. How do we execute it? How do we compile it? We need our compiler. Remember that part in the compiler main NQP where it was binding symbols? One of the symbols actually about providing the compiler itself to the rest of the code. So using NQP get comp, we can request our NQP compiler. And then this is how we compile and execute our QST code, QST tree. This argument, named argument here, specifies that our QST tree is assumed to coming out of the optimizer of static optimizer, and it is ready to be compiled into the bytecode. Because normally, if you skip this from named argument, method compile will consider this AST variable as a string, and we'll try to compile it as a string. What we get out of the compile method is a code object, and the code object we just invoke. That's it. Here's how we create a QST tree. So I hope nothing special here. Constructors of QST nodes, they're designed in a way to accept subnodes immediately. So you don't need to use extra methods. You can simply pass a list of child nodes into a parent node constructor, and you get them organized properly into a tree. This tree here, it actually represents it's the implementation of the diagram I have shown you before. This is how the diagram, I mean, this one. This is how it is implemented in code. Compiler cannot compile just any QST node. A compiler, as I mentioned earlier, a compiler operates with comp units only, with frames. So we need to create a comp unit for it. And since comp unit is just a block, this is what we do, we create a block. And then we recreate the typical structure of a block by pushing two children. First, the declaration children. Here it goes. Statements with a single symbol declaration. And the second child is body. And then we basically eval this QST tree. And out of curiosity, we dump it. And here what we get. This is output of this node, and this comes from this node. Again, details of which QST node you better find in the documentation. There are too many of them, of course. So I just wanted to make you familiar with basic ones, most used ones, like QST op, like QST var, and well, value ival in this case as well, in another case. No, in QPDI we don't need it. The only thing I would like to mention here is that you could have noticed that I use lexical scope a lot. Besides the lexical scope, a symbol declaration can have a couple of other scopes. One of them is local, which means a symbol is only available within the current frame. So if I replace this lexical here with a local, then this symbol would not be visible to any, and then insert another block child somewhere into this block, the child block would not see this full symbol. It wouldn't be available to the inner lexical scopes. Local variables are very useful when you need to speed up code, because lookup for a local variable is much, much faster than any other lookup, any lexical lookup. The other thing I have to discuss about QST and be done with them is the mutability aspect. Yes. I use about the same QST tree for this example. So if we try it, it was a better idea to do it like this. So initially we see about the same output without a dump as with the previous example. But then I have a couple of commented out lines. And here's the interesting part comes. So when the tree is built, I take our comp unit block, I remove the first declaration, the first child out of it, and then I pick another child from the middle of the second statement and call a decal on it and say var. So I basically modify the child. So what happens? I remove this child from the block, then this one becomes child number 0. Then I take child number 1. This is binding, and QP bind operation, which binds a value to a symbol. And on binding, I take another child number 0, which is this QST-var, and I turn it into a declaration. So once again, 0, 1, 0. Now, let's have a look at what we get. This is our tree before. As you can see, we have the declaration child, and we have this bind. But after the manipulation, there is no declaration child anymore. We start immediately with the body, and sorry, what did just happen? And here, as you can see, our QST-var got a new attribute, which turns it from a lexical reference node into a declaration node. So as you can see, the structure of the block, it's not mandatory. We still can declare a symbol anywhere in our code. It's just a convenience because the outcome is totally the same. Hi and 42. What happens if I remove the declaration child but don't change? We get an error, no lexical found. That's because we still have a lexical reference without any declaration of the symbol. So it's not about showing you the error message, but it is about showing you how a node can be modified in QST3. Another thing, I can change the scope of the variable. As I mentioned it before, we have lexical and we have local scope. Reset, save, yes. And try it again. Sorry. So as you can see, the first change makes it a declaration, nothing new here. But the second change is for the scope. Lexical becomes local. Sorry, I do a lot of unnecessary things. And as you can see, the result is the same. Because for this particular AST tree, it doesn't matter whether our variable is lexical or local, except that local words work somewhat faster. And it's not even a problem to change a value. So in this example, as you can see, we change first child, second child, wait a second, yes, this is designed for the original. Yes. In this example, I don't modify the block structure. So I change the first child, second child, and zero child. Let's have a look. What is it? The first child is our body. Second child, 0, 1, 2, is our say. And the first child of say is lexical reference to the symbol foo. Oh, sorry, that's 0 child. What I do here is I replace it with a QST-want node. QST-want is a special node which takes into account its scope. So if it gets invoked in string, in a string context, then this value would be used. And because say operation, it expects a string in first place, so this value would be used. In any other case, we just reuse the old QST node. The old QST node, let me remind you, is variable declaration. Within our example, this value wouldn't be used. Let's see what we have now. We have a string 42 instead of the number 42, which is bound to our lexical symbol. This is what happens when you check our static optimizer code. This is how it works. It takes the AST tree, cuts out branches, plants, grafts in other branches, and so on, and so on, and so on. Eventually, it is expected to produce QST tree, which doesn't do unnecessary work. Static optimizer, again, it's a huge subject on its own, and it's actually becomes deprecated with the RakuAST coming. So all you need to know is that it's invoked with optimize method, and same, I think, would be preserved for the next RakuAST optimizer. Okay, I did plan to show you how optimizer works, but unfortunately it's too late already, really too late. So let's finish it for today. The only thing I would like to mention here is that what advantage would RakuAST bring to us with respect to the optimization? A big problem with the current optimizer, which I can now call a legacy optimizer, is that it's not well familiar with the context of any particular query node. It's hard to guess what is the context, how this node was produced, what is surrounding it. I had to create a rather huge NQP class named operand, which does a lot of work to guess a context of a particular operand to optimize smart matching. So that if I have, say, right-hand side of a smart match, I need to know whether it's a constant, whether it's a type object, whether it's a rejects, whatever. Finding it out, it's a big problem. Not in RakuAST. RakuAST is providing you with the context as it is. You have the program, the way you have the AST tree for your program, exactly the way your program is written. So I know exactly where I am, what I'm doing, and what result I expect. That's going to be a huge advantage for the optimizer. And since we are here around RakuAST, when I was doing the previous class, I wasn't there yet, and recently I started doing some work for RakuAST as well. So maybe next time we can do a little bit of this subject as well. So some of you might be happy about it, but don't expect a lot of information either about RakuAST. I mean, it's still developing. It's not the problem about my knowledge in it, even though it's not really great yet. But the biggest problem is that RakuAST is a moving target for now. So only some introductory things. And one thing I forgot to mention during the previous class, I also said that you would need gene directory a lot, because when you get a stack trace, entries you see in the stack trace would often point back to this directory. I'm glad to say it's not true anymore. I've got NQP modified, so it now reports the real source file name, which makes finding errors much easier. Let me just explain it to you. Previously, when I was getting an error from Vault, for example, let's say something happened in this method, some bad value, whatever, add unit marker. Okay. Bad example. Okay, this one. Look at the line number 5715. Okay, not a very good example. Anyway, okay, the point is that Many files here, they're compound files. Oh, metamodel, for instance. Metamodel in QP is composed of all metamodel source files we can find in SRC Perl 6 metamodel. They're all here. So if we get an error from this file, the line number could be as big as, we see, 5,000 something. What class is it? Definite how. Okay. Here we go. So, for example, if an error happens here, line 7 of definite how MQP. Previously, you would get line 5426 from file G more metamodel MQP. So what you need to do to fix a bug, you would need to go to this file, get this line, find out what class is it, load its source file, and edit it. Find the method, find the line in this file, and edit it. Wow. I mean, it was such a waste of time. As I said, luckily, not anymore. Now you get error message coming from this file in SRC from exactly the line where it happens. So if anybody of you remember about that little issue, forget about it. It's not there anymore. And that's all for today. As you can see, I have a kind of open ending because I don't consider this course as finished, of course. As I said, we have RakuAST, and in the future, we have more subjects to consider, more advanced subjects. You choose maybe what you want to know, and hopefully I know what to tell about it. For example, we can speak about more VM dispatchers and how they work and what they can do. Those are going to be much smaller pieces, less time, I hope, because really today it's too long. Any questions? What is going to replace Vault? Helper classes. Helper classes, like for example, symbol resolving is now going to be provided by a special resolver class. So the problem with Vault, one of the problems, is that it's too big and hard to manage. Smaller chunk, better grained, more logically located. That's what RakuAST is about. Well, speaking about Gen, it doesn't mean that the directory itself is going to be gone. It's still there. We need it to compile because we still combine things together. For example, RakuAST RakuST is not compiled directly from its RakuMod source files, but each individual RakuMod file is pre-processed and put into a single RakuST file. You can find it in Gin directory as well, AST as AST-MQP. So fine, thank you everybody. And if there are no questions, then I appreciate your attention and patience, and have a great rest of your day.
Thank you.
May I have another question?
Okay, yes.
What's the difference between local and lexical scope?
Locals are not visible in inner scopes. Locals are not available to Raku code, actually. Their purpose is to provide optimized symbols for bytecode needs. That's all. For example, you can declare a lexical in your Raku. That lexical is never used in any inner scope, lexical scope. In this case, if optimizer is certain that it is not accessed and it's only used by this scope, by the scope where it is declared, then it replaces it with a local variable. And then things are working faster.
Yeah, makes sense. Thank you.
Welcome. Any more questions? Okay, then once again, thank you everybody, and see you next time. Think about the subjects you want to know about in maybe a month or so. Once again, have a great rest of your day and see you.
Enjoy.
Thank you very much. Good night.